Hello and welcome back. Did you all boogie during the dancing session? Some great tunes going on. Our last talk before our final keynote, and before I introduce our next speaker, I just want to go and thank all of the sponsors which allowed us to do this conference. Blameless, Stormforge, Teleport, Cortex, Shoreline, Lightstep, PagerDuty, Fire Hydrant, and Rootly. Thanks so much. And obviously the organizers of this event, Container Solutions. Don't forget to tweet about all the amazing talks you've heard today, what you've learned with the hashtag WTF, big letters, is, small letters, SRE, big letters. So on to our talk with Asra, with Asra, and she'll be teaching us how to salsa. Or is it, no, wait, I'm still in the partying mood from before, but Asra, thanks for being with us. Looking forward to this talk, open source project, SLSA. But I do believe you call it salsa, right?
Salsa, right? Thanks, Tim. Hi, everyone. My name is Asra Ali, and I am a software engineer on the Google Open Source Security team. So we like to call that GHOST, in addition to all of our weird acronyms like salsa. So I'm here to talk a little bit today about let's actually learn how to salsa. So I think you've heard this term at least twice today. Andy Martin gave a really awesome talk at the beginning of the day that I was tuned into and mentioned salsa. So I'm here to kind of dig in a little bit deeper, do a little bit of a demo live, and cross your fingers everything goes well. And talk to you a little bit about like what's going on in the salsa world in terms of practical salsa. So let's kind of just get right into it. Like you guys have heard like plenty of times throughout the day, software supply chain is a very pressing problem that has definitely increased in the past couple of years. And what we're kind of trying to do in anticipation of all of this is think of ways of really truly protecting our software supply chain. And what you've kind of seen throughout the talks, especially like Amanda and Sandeep kind of brought this up as well, the software delivery pipeline goes through a number of different processes and resources that go into your actual final software artifact. So at each of these stages, there's obviously places where things can go wrong. And in addition to not only things going wrong, we also, as consumers of that software, want to be able to say, oh, let's be able to kind of backtrack and see what that actual source was. Like maybe checking in random binaries into GitHub repos, downloading them, running them. Doing that is kind of scary. I'm sure anyone has kind of come across malicious malware in some way or form on the internet. And so being able to say, okay, I have a software artifact. Where does it come from? How is it built? What dependencies went into it? Where was it deployed? And all those kind of questions kind of culminate into how can I trust my software? So that's kind of what I'm going to explain. And I'm going to explain one practical problem of implementing salsa as we move through this. So like I said before, at each of the stages of the software delivery pipeline, there's places where things can kind of go wrong, starting from the developer all the way to when the client actually installs, deploys, or runs the artifact. What I'm going to focus on in this particular talk is the how to mitigate the build and deployment side of that, as well as the source portion of this. So I'm not really going to go into too much about vulnerability checks or dependencies, although that is a very important problem. And I'm sure you will be hearing much more about, dependency management and how we, maybe have a bill of materials to describe your dependencies in the, next coming conferences and things like that. But for now, I'm only really going to be focusing on how do we audit and trace back our software delivery through the build and source portion. So with that, let me kind of dive into a little bit about what actually SLSA is. So SLSA stands for Supply Chain Levels for Software Artifacts. And there's a lot of history behind coming up with a nice acronym for this that would actually turn into salsa. So there's a couple iterations about this, but in the end, what SLSA actually is a framework. So it is not a Like it is not a sort of prescriptive set of, this is how you do something. It is meant to sort of be a framework for you as an SRE or in a software engineer to kind of be thinking about your software delivery pipeline and saying, this is my threat model and this is how I want to use SLSA to mitigate it. So it kind of gives you a set of potential tools and ways of thinking about what you can actually do to mitigate these threats. So a couple of the really important parts of SLSA is generation of provenance. So provenance is metadata that describes a build. And what it will do is help a consumer or a client of that be able to audit and say, yes, I definitely know that my software was coming from this particular source, for example. And what the nice part about SLSA does is it gives you an incremental way to build up on the trust for that provenance. So we'll start, maybe just distributing provenance and having provenance be available. And then maybe we'll end at being able to roughly attest that this particular metadata was definitely unfalsifiable or non-falsifiable. So what SLSA does is kind of lay out the step-by-step manner to build more and more trust into your software supply chain. So given that, let me kind of dive in a little bit about what that build provenance and metadata is, because that's going to be like the real meat of my talk. I'm super excited to do a little demo about this. And I am pretty excited to show you some like really cutting edge work on this. So build provenance, again, like I said, provenance is a set of metadata that describes a software artifact and its procedure in getting built. So fundamentally what it does is it provides all of the inputs and process so that you as maybe an auditor would be able to say, this is exactly how that binary was built, or this is exactly how that image was built. So it gives you essentially a recipe for how to produce that particular artifact. And you can imagine if that artifact was reproducible, then this would be like an exact step where you could say, okay, I'm going to follow my procedure in the build provenance and make sure that that matches exactly what I got as well. So as an auditor or an attester, you would be able to sort of maybe certify even more trust on this provenance. But again, like I said, you can't just immediately come from a place where, okay, if I have a piece of metadata attached to my software, am I going to trust it? For example, I could say, here's a recipe to build pizza and I actually deliver to you a cake. Obviously, that's not the correct recipe. How do I actually ensure that the recipe that I'm giving you alongside the cake is a recipe for the cake that I actually gave you? So incrementally, the steps kind of go from a level 1 where I just provide you a recipe. And obviously at that stage, you have to trust that I'm actually producing the correct recipe for you. All the way up to level 4, where you have an assurance that that recipe that I gave you was definitely true and that I, even as like the delivery person involved, couldn't have tampered with that recipe. So achieving that level of trust, it's almost sort of like a zero trust game at that point, where you have no trust in the actual, even people who have access to the build system, that they were able to potentially modify that provenance statement. So I'm super excited to kind of show you how this is done in practice. So just if you want some more links about SLSA, feel free to check out salsa.dev. A couple of supply chain security con at KubeCon last October as well. There's a talk on that and a GitHub repo, and as well as if you want to get involved more in the SLSA community and ask some questions, potentially see where you can start adopting SLSA. I have some links at the end of this slide to the community meetings and Slack channels. So I want to kind of dive into how is SLSA actually done, because people love coming up with frameworks and ideas and then coming up with tools and solutions that work at scale and confidently work as well is a really tough problem, as I've seen. So as being kind of one of the people involved in creating some of these demos, there's always more to do. So we're going to start with Tekton chains. So some of you may have heard about Tekton and Tekton pipelines. Tekton chains is another project in that sort of Tekton ecosystem that allows you to create some of this provenance and allows you to sign off on that metadata. So what it aims to do is observe what's going on in your Tekton pipelines and check when something like an artifact is being created using task results. When it sees those artifacts being created, it signs off on those images, given either a public key that you provide or given some kind of identity inside the pod. So what's really interesting about this is that currently in our SLSA framework, it not only provides availability of that provenance, which is SLSA level 1, but it also achieves SLSA level 2, which is authenticated provenance, because it is signed. So I think also Andy Martin mentioned a little bit of background on digital signatures. So if you want a little recap on what digital signatures provide and how they're done, maybe recap back to that talk. But image signing is a way to guarantee that a piece of data is authentic. So what that means is we know for sure that the person who owns that key for signing endorses that exact content. So when in my sort of example of a pizza and cake delivery pipeline, if I'm the person that owns the key and I'm the delivery person and I sign off on that recipe, you know for sure that I endorse that recipe. And at least if you trust me, you can trust the recipe. But obviously, I think there's a lot more to do here, right? Like, for example, maybe you don't even want to trust me, the delivery person or the enterprise. So to do that, there's a little bit more work. But let me just dive a little bit into, like, you know, if you want more on Sigstore and Tekton, feel free to check these out. There's a really, really awesome demo by Parth Patel, this first link over here. I highly encourage you to watch that because he goes into exactly how that signing is done, and it's pretty awesome. So diving in a little bit more about where this problem of trust is. So like I said before, we're kind of currently trusting more than we might want to in certain situations. And obviously this depends on your threat model. Like I said, SLSA is a framework, so you kind of can pick and choose and decide on your particular ecosystem what you care about. So in the Tekton and SLSA world currently, what it does is it observes the task results for outputs like image digest and image URL, which you can see at the bottom of that configuration. And it observes those and then signs off on that with a provided public key, or if you're using some experimental features, with the pod identity. But like I said, there's a little bit of a problem of trust. So SLSA 2, like I said, was authenticated provenance, so signed provenance. If we want to get a little bit further into SLSA, so maybe let's not trust the delivery person or the builders as much, what we can do is maybe consider these attacks that are relevant. For example, a compromised build running at the same time might impact the provenance that you're creating for the cake. Or, for example, an insider with access to the actual builds might be able to influence that provenance statement. So again, there's still some trust that you're putting into the system at SLSA level 2. But in order to like kind of decrease that and increment our levels up one step, we have to do a little bit more work. And these are really challenging threats to mitigate. Like, as you can imagine, an insider with access to trigger builds, in most cases, they can influence the output of your provenance, you could probably imagine, right? In order to like actually prevent that from happening, you have to do a very sort of interesting way of identity management and isolation from other people. So in your build system, you have to be able to identify who that person is who's influencing outputs and identify whether or not it was someone who you expected to modify. So really the path from SLSA 2 to SLSA 3 is that SLSA 2 provides you an auditable trace of your software pipeline, given this sort of recipe that is tamper-proof. But in order to get to SLSA 3, we want non-unilateral properties of this provenance. So we want to be able to correctly determine what the like source of that artifact was in a way that even insiders or compromised builds wouldn't be able to tamper with. So that's really the crux of it. That's what I'm kind of going to show you in this upcoming demo. So in the particular case of Tekton chains, what was missing is that when we do our task run outputs and we sign off on those results, currently a cluster admin could go and change those task run statuses, and then you would get an incorrect provenance statement. So there's currently a Tekton enhancement proposal for non-falsifiable provenance support. So that is really SLSA 3 provenance. And it does this by a variety of different techniques here. And I'm going to go into a little bit about what the concepts and theories behind those two missing links are, and then show you how that's actually done. So the first missing link is about identity. So I've been kind of alluding to this before, but we need some way of identifying who is doing what in our build system. So if I'm the delivery person in my, like metaphor, I guess, we would need a way to identify that delivery person. So in the Tekton world, this is the identity of the pod. So when I'm going back to what am I signing to create this provenance, I need to make sure that the person that created those task run results was actually the intended pod. So in the Tekton chains world and in the TEP that I had linked in that previous slide, the solution that they're considering here is a Spiffy Spire solution. So this would be able to identify what pods actually modified the outputs and who are able to modify the provenance in the end. But that kind of goes back to this general problem of identity and pinpointing identity. And so I think you've heard about the Sigstore project during this conference as well today. But the Sigstore project is like one that's very near and dear to my heart. I'm a maintainer on Recore, the transparency log portion of Sigstore, and it's been a really incredible project to work through. But Sigstore's keyless OIDC-based signing provides exactly this sort of identity matching to what you're signing. So not only does it say, here's a signature on the content that proves that this content wasn't tampered with, but here's the identity behind the person that actually did the signing. So what we can do is sort of abstract that and say, okay, cool. In the Tekton world, that's going to be pod identity. In other worlds, it could just be a workload identity. So going a little bit more deep into Sigstore keyless signing, just so that we kind of have some background before I show you the examples. What it does is it requests a short-lived code signing certificate from Fulcio. So you as a developer, or you as a pod, or you as a job running in GitHub might request an OIDC token from your OIDC provider, and then send it to Fulcio, who will issue you a short-lived code signing cert that attests on the identity that's based on the OIDC token. So OIDC tokens will maybe contain an email address if they're provided from Gmail, or in the case of GitHub, it would provide your workflow information. So things like the path to your current workflow, the repository that the workflow was in, the Git SHA that it came from. So all of that identity information about your workflow is attested through that OIDC token. And then because Fulcio attests that and includes it in your X509 certificate, that information is stored inside the certificate. So what you can do with this is when you verify a signature, you can go and inspect that certificate that signed the code and say, oh, okay, this certificate contained information about the builder or the GitHub workflow or the identity that the pod was. So that's going to be our real crux of identifying who actually created the provenance inputs. That way, me as a delivery person, if I want to go and like mess with the output of the recipe, I would be denied, because you would be able to see, oh, the delivery person created that provenance statement, not the expected builder. Sorry for like drilling in this stupid metaphor. So like I said before, all of that information is stored inside that X509 certificate. And so in the GitHub case, so as I'm going to sort of like narrow down this slides into the GitHub case, I'm going to show you the GitHub demo. So Sigstore keyless on GitHub, the X509 certs look something like this, where the information of the workflow running is in the URI, and the repository information is in specific X509 extensions. So as you can see, like I have my own repository up there for my identity of the workflow. I have my calling GitHub SHA. I have the provider of the OIDC token, and I have a number of other information as well. So this is going to be our key to saying, okay, who provided the provenance? This particular builder identity and no one else. So not a compromised build, not a insider with access, but truly this particular builder. So the second key step, in addition to identifying who actually is creating inputs to the provenance, is isolation. So like I said, in order to prevent compromised builds and insiders from changing your provenance metadata, you want to be able to say the provenance generation and signing is truly isolated from both the build process and any maintainers that have access to the source code or triggers for the workflow build. So A really cool tool is reusable workflows. And GitHub released this feature, I think, back in October, November of last year. So we were super excited when it came out because we were like, oh, this is the clear missing link that we've been having. Like, how do we create SLSA level 3 provenance on GitHub and make things easy to adopt? Like, this is going to be the key. So reusable workflows are basically a mechanism of literally reusing GitHub workflows across repositories. So it's kind of callable like a GitHub action, which you might be familiar with and have used before. But instead, you call a particular repository path to another workflow. So as you can see in this example, I use the uses keyword for my particular job, and I point to a SLSA framework, SLSA GitHub generator go, and then a path to a GitHub workflow on that other repository. So then what that particular job will do is it will run all of the jobs in that reusable workflow step. So that means if you are not a owner of SLSA framework / SLSA GitHub generator go, you can't actually influence what the builder is doing because you don't have write access to that. So using this property, you can say, okay, I'm going to offload my build to this reusable workflow that's going to do the building and create some provenance and send it back to me. And I will have no way of sort of meddling with the process inside. So this gives you that guarantee of like, okay, the delivery person isn't going to modify your provenance because the delivery person has no way to sort of access that reusable workflow. So this provides that maintainer isolation. In kind of picture format here, that reusable workflow has a couple of jobs in it. It'll do the building, it'll create that provenance and sign it, and then it'll output some artifacts. Your calling workflow, so you as your developer project maintainer have no inside access into that trusted builder. That's why we end up calling it a trusted builder, because it is functionally isolated from us. So this prevents that sort of insider risk attack. The only way that insiders would really be able to sort of meddle with this process is by changing the source code inside the calling workflow, which requires review. So that's really what SLSA level 3 wants to prevent, is sort of non-reviewed meddling. So just to recap those 2 points that I mentioned, which were like key things here, we first wanted builder identity, which we achieved through Sigstore's OIDC-based signing. And then the second thing was isolation, which we achieved through reusable workflows. So this is like the key part of this. I'm going to try to demo this and kind of walk through an example GitHub workflow. All right. So here we go. So I'm going to present first the actual GitHub workflow and just kind of walk through it. In the background, I'm going to run an invocation of my workflow so that by the time that we're done with this, we can access the results. So this is the workflow that I just invoked. So this is the trusted builder that my calling workflow called. So there's going to be a couple of steps that I kind of showed in that diagram where there's first a build step and then there's a provenance and sign step. So what this workflow does is it takes a couple of inputs from the caller, including any particular environment variables, a particular argument to pass to co-publish. So this particular demo is focused on a co-build, and then the username to log into your registry, because this will also push the provenance statement and your image onto Docker or wherever else you want. And then likewise, it'll also output the location of the image. And then inside that image, we'll be able to introspect and check what that provenance statement was and check if it actually came from the repository that we expected. So the first step, obviously, is to do the build. So we're going to create a builder here. That is going to handle the actual parsing of the arguments, make sure there's nothing malicious going on, and then process the build. So we'll first run a dry run of the build, which will help us determine, okay, can we actually produce some provenance metadata without the actual build process maliciously changing the provenance? So this step is really needed to say, okay, I'm going to isolate what outputs I'm going to use and put into my provenance from the actual build process, because fundamentally, I don't really trust what's going on in the build. The second step after we do a dry run is to actually perform the build. This is going to perform the build and then also push it to my configured location. And then the final step here, like I said before, is the generation of that SLSA provenance as well as signing it. So the really cool and interesting part of it that I want to show is after generating the predicate through a generation step here, we use cosine to very, very, very simply perform the signing of the attestation. So in order to invoke cosine, all we really do is first, obviously, we need to log into the registry so that we can push our signature up to it. And then the only other thing we really need to do is run a cosine attest command to the particular predicates that we want. So this cosine experimental right here will enable us to use keyless signing and tie back that signature to the identity of this builder. So that'll be able to say, okay, definitely the image that was signed was produced inside this particular isolated builder. So that's going to give us the really crux of the decision of how do we trust the provenance. So kind of going back, let me see if our action here completed. So co-caller over here is almost done. So giving it just one more second and I will pull up my terminal over here. So kind of to just go back into it, what I'm going to use is crane and cosine commands to actually verify the attestation that I called. So awesome, everything is done here. My first step is going to be, let's go check in and see what's on my repository. So I pushed this all to hello co, which is the name of the binary that I had. And over here, you'll see that I pushed the actual image over here. I'm not going to run it because I haven't verified it yet. But you'll also see a special .at file. And that's where cosine stores our attestation, which is that build provenance statement that we had before. So what I'm going to do is I'm going to check in on that. So I'm going to do crane manifest and check in and really see what this file describes. And I forgot, because I'm in demo mode, of outputting out the JSON over here. So that's very ugly. I don't want that. But there we go. So over here, what you can see is cosine creates this manifest that contains a location of a blob with the actual attestation and the certificate that signed it. So what I'm going to do is I'm first going to show you the attestation and then also kind of show you what's inside the certificate. So what I can do is I can find the location of this blob and then use the crane blob command to check in on that. And this time I won't forget to output in JSON. But as you can see over here, here's an envelope with a payload over here. I have to go ahead and decode that with base 64. And what you'll see over here is the actual provenance statement. So this is a really awesome part of this. What you can see over here is that this is an attestation on the actual hash of the image, and it produces where that thing was actually built. So this is a provable attestation that definitely the builder was located on this particular reusable workflow. And it was built from this particular source with this particular Git SHA and with this particular entry point. So this is the entry point of the actual calling workflow. It even showed you that I did a workflow dispatch trigger as opposed to an automated one. And honestly, I think that I'm about to wrap up. The final thing that I'm just going to do is do a cosine verify attestation command. And you know what? I'm attestation. And what you will see, experimental. The demo gods got me. I am nervous as that the actual certificate signing it was coming from the builder that I had and that I was issued the token from GitHub. So I think I'm going to wrap up my demo. I hope you all enjoyed that. Awesome. All right. I think I have one more minute of questions, but let me just present my final slide and show you, some links that you can share. And obviously you can find this presentation. I'll share it with you later. But super excited to be here.
Awesome. Thanks, Asra. Really comes full circle with our first talk of the day in the DevSecOps track with Andrew Martin about who's scared of the big bad supply chain. Obviously, with a bit of salsa, you don't need to be. I know what I'm doing this weekend, playing around with salsa a little bit. I'll ask one question. What's next for salsa? What's the vision? What's coming next?
Yeah, awesome. So given that we've been able to kind of have sort of scalable, reusable workflows that provide this authenticated provenance on GitHub, what we're trying to do is integrate it into software repositories like PyPy and NPM. So that way, when you're using NPM install or you're using pip install, you'll automatically grab that provenance statement from people who are publishing artifacts and be able to say, okay, the source was coming from this particular repo. So we're super, super excited. We've been partnering with the PyPy community, and yeah, that's what's next.
That sounds very cool. Cool. Thanks again, Asra. I'm afraid we're out of time, but if anybody wants to talk to Asra, she's got her handle. Feel free to reach out. I think she might have a bit of time on the chat, but yeah, reach out and she will share the slides. And I hope you all go and do some salsa.
Yeah, go practice your salsa. Thank you so much, Tim.
Yes, thanks a lot.